And in section 3, we're going to talk about the binomial theorem. So first off, it's that when we expand any power of a binomial expression, we're going to get a polynomial. Basically, if you expand anything, you're going to get some kind of polynomial, which can be considered as a series. It's not arithmetic or geometric, but there's for sure a pattern. For example, x plus y to the power 0, well, anything to the power 0 is just going to be 1. If you have x plus y to the power of 1, you're just going to have x plus y, or 1x plus 1y. X plus y squared, well, that would become x plus y multiplied by an x plus y. And distributing everything out, you get a 1x squared plus 2xy plus 1y squared. X plus y cubed means x plus y times x plus y times x plus y. Of course, the more powers that you have, the longer it's going to take to properly distribute it out to get what we have. But there is a pattern, and there's at least 5 that we can see. The first one we can see is the number of terms. So if you're looking at it, this first line, we'll call it the 0 line, or 0th, just because of that power of 0, you'll notice that there's 1 term. Whereas on the first line, there's 2 terms. On the second line, there's 3 terms. Third line, there's 4 terms. Fourth line, there's 5 terms. Fifth line, there's 6 terms. Overall, the total number of terms is always going to be whatever the exponent is. We'll call it n plus 1. The first variable exponent. So that first variable, so the x in each of these, you'll notice that the exponents all seem to start, well, even this one is technically 0. They're always starting exactly with that power. So the x plus y to the power of 2, it's starting with an x squared. X plus y cubed is starting with an x cubed. X plus y to the power of 4 is starting with the power of 4. It always is going to start with n. And you'll notice in every single successive term, it's going from 2, then 1, and then there are no x's. This one's going from 3, 2, 1, 0. 4, 3, 2, 1, 0. 5, 4, 3, 2, 1, 0. So it actually starts at n, and then it goes down by 1. Whereas the second variable exponent, so in all of these it's a y, you'll notice the first term, there are no y's. After that, it's 1, then 2. 0, 1, 2, 3. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4, 5. It always starts at 1. And it goes to n. The sum of the exponents in each term. So meaning, in each term, this one, well, the sum of the exponents is 1. In this one, it's 2. In this one, 1 plus 1 is 2. This one's 2. This one's 3. 2 plus 1 is 3. 1 plus 2 is 3. 3. 4. 3 plus 1 is 4. 2 plus 2 is 4. 1 plus 3 is 4. You'll notice that the sum always comes up to n. So in this last term, which is x plus y to the power 5, the sum of every single term, or those exponents, always goes up to 5. Now, it is special or dependent on the binomial, but we'll talk about that in a second. And the last thing we're going to talk about is the exponents. So you can see what the numbers all are in front. We have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So we're going to write that down. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Now you might not be able to see the pattern, but there is for sure a pattern. You can see that 1 and 2 produces 3. 2 and 1 produces 3. 3 and 1 produce 4. 3 and 3 produce 6. 1 and 3 is 4. 1 and 4 is 5. 4 and 6 is 10. 6 and 4 is 10. Which means our next line, 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10, 20. 15, 6, 1. And we're actually just going to go all the way to the 8th row. 1, 7, 21, 35, 35, 21, 7, 1, 1, 8, 28, 56, 70, 56, 28, 8, 1. Every single time, and I literally set it up for this specific reason to show all this. There's a further pattern. So it's known as, this is known as Pascal's triangle. It's named after the French mathematician who described the combinations of n objects taken r at a time, which really means this. This first line, so our combinations is NCR, which can also be written as that n over r. The 0th row, 0C0, or 0C0. If you type that into your calculator, it equals 1. This next row is actually 1C0 and 1C1. This second row is 2C0, 2C1, 2C2. Then we'd have 3C0, 3C1. Oh, see, that's the first time I've done it. Didn't last day or last lesson, but you don't have to write it as a fraction. This is the better way to write it, or it's more condensed. But this one is 3C0, 3C1, 3C2, 3C3. By the time that we get to our 4th row, we have 4C0, 4C1, 4C2, 4C3, and 4C4. Then we have 5C0, 5C1, 2, 3, 4, 5. 6C1, or 0C1, 2, 3, 4, 5, 6. 7C0, and it continues on. And we're going to use that. So we're going to take into account all these patterns that are with our terms, with our variables, with our coefficients, and we're going to apply it here. So for example, we're going to use combinations in terms of coefficients in terms of the expansion of a plus b to the power of 9, which means we're just going to determine what are the numbers in front. So first off, because of that 9, it's going to start off with 9C0. Then it's going to be 9C1, and 9C2, 9C3, 9C4, all the way to 9C9. 6, 7, 8, 9. So our coefficients are going to be 1, 9. Since we already went to the 8th row, I'm just going to quickly. Alrighty. 9C2 should be 36. Apparently I can't memorize everything properly. And we'd have 84. I'm just typing this in my calculator. 9C4 is 126. 9C5, it's also 126. 126, not 216. Then 84, 36, 9, and 1. There is a reason why all of this stuff repeats itself. It always goes to your middle and then it goes back down. And it does play into effect with that, with the NCR formula. So the n factorial over the n subtract r factorial, r factorial. As we look at it, NC4, 9 factorial, 9 subtract 4 factorial, 4 factorial. Nine C4 is the exact same as 9C5. So 9 subtract 5 factorial, 5 factorial. Well, look at our denominator. 9 subtract 4 is 5. 9 subtract 5 is 4. So in both of our denominators, we have that 5 factorial and the 4 factorial. So they will be the same thing because our numerators are already the same. So that's just kind of a side note information, as our combinations are going to repeat. Permutations only repeat at the very end, and didn't say it when we did our permutations, but long story short, 0 factorial is 1. Can't remember the specific reason for it, but it just is. Okay, so now let's actually have all of this a plus b to the power of 9 expanded. So of course, you could go the long way. You could take a plus b multiplied by a plus b multiplied by a plus b all the way 9 times, expand everything out, or we could do it the quick way. And the quick way is literally taking 1 in front. Sorry, I'm going to write it this way. I'm going to go one step at a time. We're going to have 9C0 as our coefficient. We are then going to take a, which is that first term, to the power of 9. We're going to take that positive b to the power of 0. We are going to add 9C1. A to the power of 8, b to the power of 1. Because that first term, that a is going to start at 9 and it's going to go down. Our second term, our b, is going to start at 0 and it's going to go up. Just like we had noticed the pattern in this. Our first variable goes down goes down by 1. Should probably add it to 0 and starts at 1 and goes up by 1. Sorry, should probably include that a little bit. Some of exponents is n. We'll have n plus 1 terms, which we will. But here is what we're going to do. So this is the long form, and we're going to be doing this in some other ones. So a to the power of 7, b to the power of 2. So notice how that first term, that a, starting at 9, and it's going to go down. So 9, 8, 7, the next one will be 6. The b is going to start at 0, 0, 1, 2, and go up. So 9C3, a to the power of 6, b to the power of 3. 9C4, a to the power of 5, b to the power of 4. 9C5, a to the power of 4, b to the power of 5. Again, noticing, at the same time noticing that the sum of these exponents are going to be 9. 4 plus 5 is 9, 6 plus 3 is 9, 7 plus 2 is 9. And second time, okay. 9c6, a to the power of 3, b to the power of 6. 9c7, a to the power of 2, b to the power of 7, 9c8, a to the power of 1, b to the power of 8, and 9c9, a to the power of 0, b to the power of 9. So it looks long and convoluted, and we're going to use, I'm not going to give you long ones to the power of 9. Usually the highest one that I will go to is to 6. So meaning 7 terms. You can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 terms, which is exactly how many we need. Let's write it all out. So overall, this is actually infinitely shorter amount of time than it would take to expand all of this. Trust me. 9c0 is 1. We already had done all those calculations here. A to the power of 9 is just a to the power of 9. B to the power of 0 is 1. So you don't have to write b to the power of 0. 9c1 is 9. A to the power of 8, b. 9c2 is 36. A to the power of 7, b squared. 84. A to the power of 6, b to the power of 3. 126, a to the power of 5, b to the power of 4. Then we'd have 126, which is 9c5, a to the power of 4, b to the power of 5. 84, a to the power of 3, b to the power of 6. 36, a squared, b to the power of 7. 9, a, b to the power of 8. And 1, no, we're not going to need a to the power of 0. B to the power of 9. That would be this entire binomial fully expanded. Yes, it takes time. But at the same time, this is going to take a way shorter amount of time. So now we're going to apply that same bit of stuff to this one. We have a power of 5 though. So we're going to have 5c0 as our coefficient. This question is a little bit different because our first and second term are a bit different. Our first term is still okay. It's going to be b to the power of 5. But our second term is going to be this entire negative 2c to the power of 0. The second term, 5c1, b to the power of 4, negative 2c to the power of 1. I'll let you know in this one, we're going to actually have 2 steps in here because we're going to have to do a bit more work, especially with these exponents. Then we have 5c2, b to the power of 3, negative 2c to the power of 2. 5c3, b squared, negative 2c to the power of 3. 5c4, b to the power of 1, negative 2c to the power of 4. And finally, 5c5, b to the power of 0, negative 2c to the power of 5. I'm going to show you the intermediate step, because we don't have everything calculated out, as well as we have to actually apply some exponents here. 5c0 is 1. We're going to be multiplying by b to the power 5. Multiplied by negative 2c to the power 0. Well, by our exponent laws, anything to that power 0, like we had done in grade 9, is 1. 5c1 is 5. B to the power 4 is b to the power 4. I'm going to just put in brackets just to kind of keep things separate. Negative 2c to the power 1, though, is negative 2c. And that's where things are going to start changing. 5c2 is 10. We'd have b cubed. Negative 2c to the power 2 means negative 2 squared, which works out as 4, and c squared, which is c squared. 5c3 is also 10. b squared. Negative 2c cubed means negative 2 cubed, which is negative 8. C cubed. C cubed. 5c4 is 5. b to the power of 1. Negative 2c to the power of 4 is 16. C to the power of 4. 5c5 is 1. B to the power of 1, or b to the power of 0 is 1. And negative 2c to the power of 5 is negative 32 c to the power of 5. So to our final step and our final answer, well, just like we've been doing with any kind of monomial before, we multiply numbers together and we multiply our exponents together. So 1 times 1 is just going to be 1. Technically, obviously, you don't have to write that, but then you'd have b to the power of 5. Positive 5 multiplied by negative 2 is negative 10. And that is where things start changing. Because our binomial is not just an a plus b or an x plus y, like this one or the one that on the front page, our question is going to differ greatly. But the similar procedure that we're doing here isn't going to change. We're just going to have negative 10 b to the power 4c, which means it's just that 5 multiplied by the negative 2 there. Plus 10 times 4, which is 40, b cubed, c squared. 10 times negative 8 is negative 80, b squared, c cubed. 5 times 16 is a positive 80. b, c to the power 4, subtract 1 times 1 times negative 32, which is negative 32, c to the power 5. A lot of our patterns still stick, like our sum of our exponents, 5, 5, 5, 5, 5, 5. Our coefficients have drastically changed though. But the same procedure that we had done with something that's really long and convoluted can be applied to this one. At the same time, you can notice a few different things. For example, there's 6 terms, which is 5 plus 1. And I'll bring back one other kind of pattern that will apply from here down to here. So we want to, in this question, we're going to find the 9th term. Okay, we have 2 questions on here. So the 9th term of 3z subtracting 2w to the power of 12 is going to be determined by 3 different things. Our coefficient, which is then going to be multiplied by the first term, which is then going to be multiplied by the second term. What I mean by first term is at 3z, and our second term is at negative 2w. Our coefficient is going to be 12c, let's see, 9th term. Well, if we look at it, we can see that all of our combinations always start at 0, which means our 9th term would be a 12c8. Of course, if you do write it as 12c8, I would never mark it wrong. It's just this is the kind of the shorter way of writing it. Our first term. This one's going to be the tricky one. But at the same time, if we actually do our second term first, it's going to help us do this first. So if we skip from coefficient to our second term, and then we come back, it's actually going to, we're going to see some interesting stuff here. And that's what I mean here. I'm going to show you another pattern. Let's take a look at our question here. What is the connection between our coefficient and our second term? Coefficient, second term, coefficient, second term, coefficient, second term. Hopefully, if you're looking at it, you'll notice that our R value is the exact same as what the exponent is in that second term. 5c4, that negative 2c is to the power 4. Which means we'd have a negative 2w to the power of 8. Why does that then help us with our first term? Well, our coefficients have to add up to be, in this first question, or this question, had to add up to be 5. Because that was what our exponent is. Our exponent here is 12, which means that first term, that 3z, would have to be a 4. Then further, we can just rock and roll. 12c8, 495. We're going to multiply it by 3z to the power 4. Well, 3 to the power 4 is 81. Z to the power 4 is z to the power 4. Negative 2w to the power of 8, say negative 8 times means it's going to be positive. 2 to the power of 8 is 256. W to the power of 8. To get our final answer, multiply the coefficients. 495 by 81 by 256. That's fun. 10,264,320. Z to the power of 4, W to the power of 8. No, a question like this, obviously with 13 terms, I would never make you fully expand this out. But it is still fun to see and identify. Okay, if 120 x of, next question. If 120 x to the power of 7, y to the power of cubed is a term in the expansion of x plus y to the power of n, what's the value of n? Hopefully you can quickly read. The answer should be 10. Because 7 plus 3 is 10. That's all it has to be for that question. How about, how many terms would be in a plus b to the power of 51? Well, it's just going to be 51 plus 1. We're always going to have one more term than what our exponent is. If 252 x to the power of 5 n to the power of n is a term in the expansion x plus y to the power of 17, what's the value then? 17 subtract 5 is 12. So some of these questions are really quick. Even this one, I don't even need this much space. Because we had seen that pattern in this previous question here about all of this stuff. We want to determine what our coefficient is if we have x to the power of 5, y to the power of 10, and it's in the expansion of x plus y to the power of 15. It's going to be 15c10 because of that 10. And 15c10 3003. So last one, which is, this one's going to kind of toss you a little bit because we're going to have to apply a bit more exponent laws. And it's just for the fact that our variable a, we could use x. Yeah, we'll stick with a for now. I'll make sure on your unit assignment it has x. But our a is in both terms. So it's going to mess with what our exponent is. But we're still going to apply the same bit of information. Still going to apply the same principle, same procedure. 5c0, a squared to the power of 5. So this is already going to mess things because we have something that's different than just a single term or a single degree 1 in each of these. All of our other questions have had a z or a w or an x or a y or an a or a b. Well, now we have an a to the power of 2. And we even have a 1 over a, which, if you remember back to our Foundations 10, is an a to the power of -1, which will kind of come into effect when we do simplify. But then we're going to have that -1 over a to the power of 0 plus 5 over 1, a squared to the power of 4. So I try my best to come back to the same kind of skills that we've done before. And we're just going to apply them. A squared cubed, -1 over a squared. 5c3, a squared, squared, not cubed. Because that first is going to go 5, 4, 3, 2, 1, 0. The second one is going to go 0, 1, 2. Then we'd have -1 over a to the power of 3. 5c4, a squared to the power of 1, -1 over a to the power of 4. 5c5, a squared to the power of 0. At this point in time, you may ask yourself, why are we writing this to the power of 0? Because it's just going to equal 1. I would like you to do it just so you don't forget about it. If you have to write it, then you're not going to forget about it. And that's what I don't want. I don't want you to forget. I don't want you to forget terms. Or in this case, specific parts of terms. Okay, 5c0 is 1. A squared to the power of 5, well, an exponent with an exponent means we're going to multiply those exponents. So a to the power of 10. If you were thinking a to the power of 7, well, it's a good thing that we explain our exponent laws again. 5c1 is 5. A squared to the power of 4, just like before, will be a to the power of 8. -1 over a to the power of 1 is going to be a -1 over a. 5c2, for some reason I think this fifth row is the one that I know the best. A to the power of 6. -1 over a squared, well, a negative squared is going to be positive. So we'd have 1 squared, which is going to be 1, and a squared, which is going to be a squared. 5c3 is 10. A to the power of 4. -1, so negative cubed is going to be negative. 1 cubed is 1. A to the power of 3 is a to the power of 3. 5c4 is 5. A squared to the power of 1 is a squared. Negative to the power of 4, positive. 1 to the power of 4, 1. A to the power of 4, 4. And 5c5 is 1. A squared to the power of 0 is 1. And negative to the power of 5 is negative. 1 to the power of 5 is 5, or 1. A to the power of 5 is a to the power of 5. All right, to get to our final answer, 1 and 1 is 1. Obviously, you don't need to write the 1, but I do just because I can. Positive 5 and a negative 1. Oh, negative. I should have known that because I'd have to draw back one more pattern. 8 to the power of 8 with an a in our denominator means that it's going to reduce. We'd have 8 to the power of 7. So this is what I have meant with our exponents are going to get a little bit messy because it's not going to go with sums to 5 because we had that first off because of the a squared, and the second off we had that a in our denominator. We had two of the same variable. If this was a b, it would probably be relatively fine as well, but because of that a squared and that our coefficients, our exponents are going to be vastly different. So you can't always rely on it being equal. But these questions like this, I will always just, because it's part of the curriculum that you have to identify these patterns. These ones, to try and draw back to our exponent of 5 here, well, there's only one way you can do it, and it's the fact that there's going to be 6 terms. But overall, it's still good to go. Okay, 10 and 1 is 10. A to the power of 6 and a squared. Well, 2 of them are going to cancel off, which means we're going to be left with 4. So a to the power of 4. Subtract, because 10 and negative 1 is going to be negative 10. A 4 and 3 of them are going to be left with 1 of them. Let's see, we're going to add a 5. And this is where I'm going to show you 2 different ways that you can do it. We could cancel out both of them here, be left with 2 of them there, which means we'd have 5 over a squared. And I'll show you the alternative way in just a second. Subtracting, because 1 times negative 1 is going to be negative, and we'd have it as 1 over a to the power of 5. The alternative way of writing it, these 2 terms could be a 5a to the power of negative 2, subtracting a to the power of 5, negative 5. Because them being in the denominator, to move it to the numerator would be negative. So everything else would stay the exact same. 1a to the power of 10, subtracting 5, a to the power of 7, adding 10, a to the power of 4, subtracting 10a. But then just we'd have negative exponents. I don't care which way you write it, because to me, they're both the same. If you're going calculus, this is going to be your better method. Otherwise, this is perfectly fine with me. Okay. One last thing I wanted to show you is you'll notice a pattern of how the terms are actually written. You'll notice that this is positive, this is negative. Positive, negative, positive, negative. This will always happen if you have a subtraction in between your 2 terms. Addition, subtraction, addition, subtraction, addition, subtraction. Even on the previous page, this was a subtraction in between. Addition, subtraction, addition, subtraction, addition, subtraction. Always will work out that way. But that's only first, obviously, if there's a subtraction. When there's an addition in between, it's all going to be addition. Alrighty, that leaves you some time. You'll see some questions in here. There's some patterns that you can kind of see in grade 10, or not grade 10, in question 10 and in question 21. So I just wanted you to kind of take a look at it, see what the kind of patterns are. For example, there's some, I think one of them is an L pattern that you can kind of see, which really ties closely into what we see here. But I just want you to take a look. And obviously, have some fun.